It was a Sunday morning. The sky above the Pacific Northwest was clear, that particular blue that follows days of overcast, sharp and cold and absolutely still. A 30-year-old man stood alone on a ridge, 5.5 miles from a mountain he understood better than almost anyone alive. He had chosen to stay. The night before, when they offered him the chance to rotate out, to let someone else take the post, to sleep somewhere safer, he said no. There was work to do. There were readings to record. The mountain was saying something, and someone needed to be close enough to hear it. At 8:32 in the morning on the 18th of May, 1980, the entire north face of Mount St. Helens ceased to exist. Not in flames, not gradually, all at once. And the man who was watching, the only human being with a clear, unobstructed view of what was happening in that exact moment, did the only thing a scientist of his character could do. He reached for his radio. What he said next would travel 57 miles in seconds. And then his voice was gone forever. How does a mountain kill in silence? And why did he choose to stay? That is the story we are about to tell you. There are places on this earth where the ground itself remembers, where the rocks beneath your feet hold a memory older than any civilization, older than any written word. A memory of fire. The Pacific Northwest of the United States is one such place. To those who lived in its shadow, Mount St. Helens was simply the mountain. A presence. A neighbor. A perfect white cone rising nearly 10,000 feet above the forests of Washington state, reflected in the mirror of Spirit Lake below. Painters came to capture it. Poets wrote of it. Children grew up knowing its silhouette the way they knew their own hands. It was beautiful. It was serene. It was, to all outward appearances, asleep. But sleep, in geology, is not the same as peace. Mount St. Helens belongs to the Cascade Range, a long spine of volcanoes stretching from northern California through Oregon and Washington, all the way into British Columbia, Canada. Born from the slow, relentless collision of tectonic plates deep beneath the Pacific Ocean, these mountains are not decorations on the landscape. They are pressure valves.
Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes.
Cascades had spoken before. Mount Lassen, in California, erupted as recently as 1915. The indigenous peoples of the Pacific Northwest carried oral traditions stretching back thousands of years. Stories of mountains that shook, that burned, that changed the sky. The Klickitat people called Mount St. Helens Luwala Klo, the Smoking Mountain. A name earned, not invented. For most of the 20th century, however, the mountain gave no cause for alarm. Generations of loggers, fishermen, and families built their lives in its shadow. Spirit Lake became a beloved retreat. Summer camps, fishing cabins, the quiet sound of water against a wooden dock on a cool morning. A man named Harry Truman, no relation to the president, had run a lodge on Spirit Lake since 1928. He was 83 years old, stubborn as the mountain itself, and deeply, completely at home there. He would say, when people later urged him to leave, "That mountain is a part of me, and I'm a part of that mountain." He meant it. What no one fully understood in those comfortable decades was that the mountain had a history of extraordinary violence. Geologists studying its ancient layers found evidence of massive eruptions that had reshaped the landscape, buried forests, sent ash across a continent. The last great eruption had ended around 1857. Just over a century of silence. In geological time, that is barely a breath. And in the late winter of 1980, something began to stir beneath the ice and the snow and the ancient stone. Something that had been patient for a very long time. Next, We follow the first tremors, and the scientists who began to listen. It began with a whisper. On the 20th of March, 1980, a small earthquake, magnitude 4.1, rippled beneath the foundation of Mount St. Helens. By itself, it might have been nothing. The Pacific Northwest lives with earthquakes the way coastal towns live with tides. A tremor here, a rumble there. But this one was different. It did not stop. Over the days that followed, the earthquakes came in waves, dozens per day, then hundreds. Seismographs at the University of Washington scratched their silent testimony onto scrolling paper, line after restless line, each one a heartbeat of something enormous waking beneath the stone. Scientists had instruments now that previous generations could only dream of. They had seismometers and tilt meters and aerial observation flights. They had the tools to listen. And the mountain was speaking clearly. On the 27th of March, Mount St. Helens exhaled for the first time in 123 years. A column of steam and ash rose nearly 6,000 feet into the cold Washington sky. A crater had opened near the summit, small by volcanic standards, barely 100 feet across. But it was there, dark and smoking against the white snow. The mountain had opened its eyes. The United States Geological Survey, the USGS, moved quickly. Scientists and volcanologists were dispatched to the region. Equipment was installed. Observation posts were established at what were believed to be safe distances from the mountain. Among those who arrived in those early weeks was a young geologist named David Johnston. He was 30 years old. He had studied volcanoes with the devotion that other men reserve for cathedrals. His doctoral work had taken him to Alaska, to the volatile peaks of the Aleutian Islands, where he had learned, viscerally, personally, what it meant to stand near something that could kill without warning. Those who knew him described a man of quiet intensity, careful, methodical, someone who chose his words the way a surgeon chooses instruments, with precision and purpose. He was also, by all accounts, genuinely joyful in the presence of volcanoes. Not reckless, never reckless, but alive in a way that only comes when a person has found the exact work they were meant to do. Johnston understood, almost from the beginning, that Mount St. Helens was not simply restless. It was dangerous in a particular and troubling way. Most volcanic eruptions follow a relatively predictable path. Pressure builds. Lava finds a vent. The mountain exhales upward, dramatically but vertically, giving those below at least the theoretical possibility of escape. But Johnston had studied what geologists call a lateral blast, an eruption that does not go up, but sideways. An explosion directed outward, like a cannon fired horizontally, releasing its energy not into the sky, but across the landscape. The evidence was there in the mountain's own ancient layers. It had happened before, here, on this very peak. He wrote in his notes that the volcano represented, in his words, a very dangerous situation. He was not given to exaggeration. Through April and into May, the mountain continued its slow and ominous transformation. A bulge appeared on the north face. This was, to the trained eye, profoundly alarming. Magma, molten rock under tremendous pressure, was pushing upward and outward from within, deforming the mountain's slope the way a blister rises on skin. Each day, surveyors measured the bulge's growth. It was expanding at a rate of 5 to 8 feet per day. 5 to 8 feet. Every single day. Inside that swelling slope, pressure was accumulating on a scale almost beyond comprehension. The north face of Mount St. Helens was becoming, in geological terms, a loaded weapon. The exclusion zone around the mountain was established. Roads were closed. Residents were urged, sometimes ordered, to leave. Some left. Some, like Harry Truman at his lodge on Spirit Lake, refused absolutely. And the scientists remained too, at their posts, at their instruments, doing the work that science demands even when, especially when, the situation is frightening. David Johnston was assigned to Coldwater 2, an observation post on a ridge approximately 5.5 miles from the summit of Mount St. Helens. It seemed at the time far enough. The mountain was ready. The scientists were watching, and the 18th of May was approaching. There is a particular quality to the silence that precedes catastrophe. It is not peaceful. It is not empty. It is the silence of held breath, of something enormous gathering itself, of pressure finding its geometry, of the world pausing in the last moment before everything changes. In the days leading up to the 18th of May 1980, Mount St. Helens wore that silence like a mask. The earthquakes had actually quieted somewhat in the preceding days. To the untrained eye, this might have suggested reassurance. Perhaps the mountain was settling. Perhaps the worst had passed. But to David Johnston and his colleagues at the USGS, the relative calm was not comforting. It was suspicious. Volcanoes do not announce their intentions politely. They do not send formal notice. And a volcano that has been building pressure for weeks, that has deformed its own face by hundreds of feet, that carries within it a reservoir of superheated magma, that volcano does not simply decide to rest. It waits. The 17th of May passed quietly. Johnston rotated through his shift at Coldwater 2, the observation post perched on a ridge to the northwest of the mountain. The post was modest: a camper trailer, radio equipment, instruments recording the mountain's vital signs around the clock. From that ridge, the view of Mount St. Helens was extraordinary. The great north face bulge was clearly visible even from 5.5 miles away. A distortion in what had once been a perfect cone. The mountain looked, to those who studied it, like something straining against its own skin. Johnston recorded his observations. He communicated with colleagues. He did his work with the steady, unhurried professionalism that those who knew him would later remember as his defining quality. That evening, he was offered the opportunity to rotate out, to let another geologist take the Coldwater 2 post for the following day. He chose to stay. The reasons a person makes such a choice are never entirely simple. Duty, certainly. Johnston took his responsibilities seriously. But there was also, perhaps, something else. That quality of deep engagement that marks a scientist who is exactly where the science is happening. The mountain was at its most active, its most revealing. To leave now would have felt, to a man like Johnston, like walking out of a conversation at its most important moment. He stayed. That night, under a sky that offered no particular warning, he slept in the camper at Coldwater 2. 5.5 miles from the north face. 5.5 miles from the bulge. 57 miles to the south, in the city of Vancouver, Washington, the USGS Cascades Volcano Observatory hummed with quiet activity. Scientists monitored incoming data through the night. The instruments told them the mountain remained restless beneath its surface calm. Pressure readings, tilt measurements, seismic signatures, all of it pointing toward the same conclusion that Johnston had articulated weeks earlier. This was not a mountain that was going back to sleep. The morning of the 18th of May arrived slowly, the way spring mornings do in the Pacific Northwest. Cool air, a sky of particular clarity, the kind that follows days of overcast, sharp and blue and impossibly clean. It was a Sunday. At Coldwater 2, Johnston was awake and at his instruments before dawn. The radio crackled with routine communications between observation posts, scientists checking in, exchanging readings, maintaining the patient vigil that volcano monitoring demands. Harry Truman, 8 miles from the summit at Spirit Lake, was almost certainly making his morning coffee. 57 people remained within the general vicinity of the mountain that morning. Some scientists, some journalists who had obtained special permits, some stubborn residents like Truman who had simply refused every warning offered to them. The exclusion zone had kept thousands more at a safer distance, but safe, as Johnston knew better than almost anyone, is a word that requires constant revision when you are dealing with a volcano. At 8:31 in the morning, a magnitude 5.1 earthquake struck directly beneath the north face of the mountain. It lasted only a few seconds. It was enough. The bulge, that vast, trembling accumulation of displaced rock and pressurized magma, lost its final argument with gravity. The entire north face of Mount St. Helens began to move. What happened in the next few seconds would rewrite volcanology. It would confirm Johnston's darkest assessments. It would become one of the most studied, most documented, most scientifically consequential geological events in recorded American history. And David Johnston, at his post on the ridge, had a direct and unobstructed view of all of it. He reached for his radio. The mountain has moved, and a voice is about to cross 57 miles of open air. There are moments in history that arrive without ceremony. No drum roll, no formal announcement, no final opportunity to prepare. They simply happen, sudden and absolute, and the world that existed 1 second before is gone forever. At 8:32 in the morning, on the 18th of May, 1980, David Johnston experienced one of those moments. And he did what scientists do. He reported it. The north face of Mount St. Helens did not explode in the way most people imagine an explosion. It did not erupt upward, sending a column of fire into the sky. It did not give those watching a dramatic, cinematic moment of obvious danger approaching from a distance. It collapsed. The entire north flank, a volume of rock and ice and compressed earth equivalent to 1 cubic mile of material, simply gave way. In geological terms, it was the largest landslide ever recorded in human history. A wall of debris moving at speeds approaching 150 miles per hour, cascading down the mountain's face and into the valley below. And the moment that landslide released the pressure that had been building for 2 months, the volcano beneath detonated. Laterally, outward, directly toward David Johnston. What volcanologists call a lateral blast is not, in the ordinary sense, a blast at all. It is more accurate to describe it as a wave.
Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes.
A superheated wave of gas and pulverized rock traveling at speeds that, in those first seconds, approached the speed of sound. Temperatures within that wave reached estimates of more than 600 degrees Fahrenheit. It carried everything before it. Ancient trees, Douglas firs that had stood for 2 centuries, were not burned. They were not pushed over. They were snapped like matches and deposited in neat, terrible rows pointing away from the mountain, a forest laid flat across 230 square miles of landscape. The blast zone was not a circle. It was not even roughly symmetrical. It was a fan shape, directed northward, carved by the geometry of the collapsing flank. Coldwater, too, sat directly within that fan. In the seconds between the landslide and the arrival of the blast wave, David Johnston would have seen something no human being had ever witnessed from so close a distance and survived to describe. The north face of the mountain disappearing. A rolling, churning cloud of gray and brown and white erupting outward from where the rock had been, expanding visibly, rapidly, filling the valley below and climbing the ridgelines with a speed that defied the eye's ability to process it. He would have understood immediately what he was seeing. He had spent years studying this precise phenomenon. He knew exactly what it meant. And still, he reached for the radio. "Vancouver! Vancouver! This is it!" 6 words, transmitted at 8:32 and 47 seconds in the morning to the USGS office in Vancouver, Washington, 57 miles to the south. The voice that spoke them was calm. Not the calm of a man who did not understand his situation. Not the calm of someone who believed he might survive what was coming toward him at the speed of an oncoming freight train multiplied many times over. It was the calm of a scientist completing his final observation, of a man who had chosen, the night before, to stay at his post. Of someone who understood that the data he was transmitting in those last seconds, the confirmation that the lateral blast had begun, that the mountain had finally released what it had been holding, was information that mattered, that would save lives, that would change volcanology forever. At the USGS office in Vancouver, the radio operator heard the transmission clearly. Then the signal went silent. Not with static, not with the gradual fade of a failing battery or a moving vehicle passing out of range. Simply silence. The kind of silence that arrives all at once and stays. Colleagues who were present in that room in the moments after Johnston's transmission have described, in the years since, the particular quality of that silence. How it differed from ordinary radio quiet. How everyone in the room understood, without anyone saying so, what it meant. They tried to raise cold water too. There was no answer. There would never be an answer. The blast wave reached Johnston's position in approximately 15 to 30 seconds after the lateral explosion began. 15 to 30 seconds. The time it takes to read a short paragraph, to pour a cup of tea, to look out a window and back again. His camper trailer, his instruments, his careful notes, all of it was gone. The ridge itself was scoured to bare rock. When search teams eventually reached the area, weeks later, they found fragments, pieces of equipment, nothing more. David Johnston's body was never recovered. He was 30 years old. He had given his life not through recklessness, not through failure of judgment, but through the precise application of scientific duty. He had stayed at a dangerous post because the science required it. He had transmitted his final observation because that is what the work demanded. In the seconds he had, he chose to speak. And the words he chose were not farewell. They were not fear. They were data. A mountain has erupted. A voice has gone silent. And now the world must reckon with what was lost and what was learned. When Mount St. Helens finished what it had started, the world above it ceased to exist. Not metaphorically, not poetically, literally. The sky above the Pacific Northwest on the morning of the 18th of May, 1980, was erased. The eruption column that rose from the collapsing mountain in the minutes following the lateral blast climbed with a violence that meteorologists would later struggle to adequately describe. Within 15 minutes of the initial explosion, the ash column had reached 80,000 feet, nearly 16 miles above the Earth's surface. It had punched through the troposphere, through the stratosphere. It was visible from commercial aircraft cruising at 30,000 feet, and still it rose above them. At its peak, the eruption was releasing energy equivalent to 27,000 Hiroshima atomic bombs. Not in total, not across the entire event, per second. Below that column, the landscape was undergoing a transformation so complete that the word destruction feels insufficient. The landslide that had triggered everything, that 1 cubic mile of displaced mountain, had traveled northward into the Toutle River Valley at speeds that left no room for anything living to respond. It buried the valley floor under deposits reaching depths of 600 feet in places. It transformed a river system into a vast, steaming plain of gray debris. Spirit Lake, where Harry Truman had lived for 52 years, was buried under hundreds of feet of rock and ash and displaced water. The lake itself was gone. Harry Truman was gone with it. He had refused every warning. He had loved that mountain with the absolute, unreasonable devotion of a man who had built his entire life in one place. And the mountain, indifferent as only nature can be indifferent, had kept him there permanently. His body, like Johnston's, was never found. The ash cloud moved east. This is the aspect of the eruption that most Americans living beyond the immediate blast zone came to understand personally. Not as a news story, but as a physical experience arriving at their doorstep. Ash falls differently than rain. It does not announce itself with sound. It arrives in silence, a fine gray powder that settles on everything with a patience that feels almost deliberate. It coats leaves and windowsills and parked cars. It turns afternoon into a darkness deeper than any natural dusk. In Yakima, Washington, 140 miles to the east, daylight vanished by mid-morning. Streetlights activated automatically, responding to sensors that believed night had arrived. Residents who stepped outside found the air thick with fine particles, the smell of something ancient and mineral, a quality to the atmosphere that had no equivalent in ordinary experience. Schools closed, airports shut down. Roads became impassable. The ash continued east through Montana, into Idaho, into Wyoming, and beyond. Within 2 weeks, measurable deposits of Mount St. Helens ash were recorded across the entire continental United States. Within 2 weeks after that, traces had circled the Earth. For those within the immediate region, the hours following the eruption carried a particular disorienting quality of unreality. The landscape that had existed that morning was gone. Forests that had taken centuries to grow, 230 square miles of ancient timber, had been stripped from the earth in less time than it takes to cook a simple meal. The area around the mountain looked, to those who saw it from the air in the days that followed, like the surface of the moon. Gray, featureless, absolute. Geologists who flew over the blast zone in the immediate aftermath reported a collective, sustained silence in their aircraft. Not because there was nothing to say, but because the scale of what they were seeing exceeded the vocabulary available to them in that moment. There are experiences that language must approach slowly, from a respectful distance. This was one of them. 57 people died on the 18th of May, 1980. Each of them a life fully lived, fully particular, fully irreplaceable. Some were scientists. Some were journalists. Some were residents who had refused to leave. Some were simply people who had gone to the mountain on a spring morning because it was beautiful, because it was familiar, because nothing in their experience had prepared them to imagine what was about to happen. 57. It is, given the scale of the eruption, given the energy released, the area affected, the absolute completeness of the destruction within the blast zone, a number that reflects something important. The warnings had worked. The exclusion zone, imperfect and contested as it had been, had kept thousands of people at distances that saved their lives. The scientists who had argued for broader evacuations, who had insisted on taking the mountain's behavior seriously when others counseled patience, had been proven terribly, irrefutably correct. David Johnston had been among the loudest of those voices. In the hours after the eruption, as ash fell on half a continent, and rescue teams began the slow, dangerous work of assessing what remained, the radio at the USGS office in Vancouver sat quiet. Coldwater 2 did not transmit again. But the data Johnston had gathered in the weeks before, his measurements, his assessments, his careful and insistent warnings, those did not go silent. They became the foundation of everything that followed. The mountain has spoken. The world has listened. And now, science must make sense of what the Earth has revealed. In the weeks that followed the eruption, a strange and difficult task began. Not rescue. There was very little left to rescue. Not reconstruction. The landscape that had existed was gone so completely that reconstruction was not yet a meaningful concept. The task was understanding. Scientists, geologists, ecologists, and volcanologists descended on the region with instruments and notebooks and a kind of disciplined grief. The grief of people who had lost colleagues, who had witnessed devastation on an almost incomprehensible scale, and who understood that the only appropriate response available to them was to learn everything the mountain was willing to teach. The physical transformation of the landscape was, in purely geological terms, extraordinary. The summit of Mount St. Helens had lost approximately 1,300 feet of elevation in a single morning. A mountain that had stood at 9,677 feet above sea level now rose to only 8,363 feet. Where a perfect, symmetrical cone had reflected in the surface of Spirit Lake, there was now a vast, open crater, horseshoe-shaped, facing northward, raw and smoking and entirely new. Geologists walked the blast zone with the careful attention of archaeologists at an excavation site. Every layer of deposited ash and debris told a story. Every snapped tree told a story. The direction of the fallen timber, the depth of the ash deposits, the chemical composition of the erupted material, all of it was data. All of it was evidence of processes that science had theorized but never observed at this scale, with this degree of instrumentation, in a country with this capacity to study what had happened. Mount St. Helens had not merely erupted. It had performed, under observation, one of the most complete volcanic sequences ever documented. Among the most significant findings were those that confirmed what David Johnston had feared most deeply. The lateral blast, the directional, horizontal explosion that had defined the eruption's first and most devastating moments, had behaved precisely as Johnston's models had suggested it might. The physics were now undeniable. The evidence was written across 230 square miles of flattened forest. A volcano did not need to erupt vertically to be catastrophic. It did not need lava flowing down its slopes. It did not need the classical, cinematic image of a mountain spewing fire upward into the sky. It needed only a destabilized flank, a sufficient accumulation of pressure, and a trigger. The earthquake on the morning of the 18th of May had provided that trigger. Johnston had understood this. He had written about it, argued for it, used it as the scientific basis for his insistence that the exclusion zone needed to be broader, that the mountain represented a danger not merely at its base, but across a wide lateral arc to its north. He had been correct in every particular. The human cost of the eruption extended beyond the 57 who died on that single morning. In the months that followed, the Toutle River, choked with volcanic debris, became a slow-moving disaster. Sediment flows damaged bridges and navigation channels miles from the mountain. The Columbia River, into which the Toutle drains, was partially blocked, disrupting shipping traffic. Agricultural land downstream was buried or contaminated. The economic damage across the region ran into billions of dollars. Communities that had defined themselves by the timber industry found their forests gone. Fishing communities found their rivers transformed. Towns that had welcomed tourists drawn by the mountain's beauty found themselves receiving instead scientists and journalists and the merely curious. People who came to look at absence, at erasure, at what a landscape looks like after nature has rearranged it without consultation. And yet, within the devastation, something unexpected was beginning. Life. Not immediately, not dramatically, but with the quiet, insistent persistence that characterizes living things when given the smallest possible opportunity. The first species to return to the blast zone were not the ones scientists predicted. Pocket gophers, burrowed beneath the ash during the eruption, emerged and began turning over the soil. Wind carried seeds from the forests at the blast zone's edges. Lupine, a flowering plant with the remarkable ability to fix nitrogen into barren soil, appeared in the gray landscape within a year, small purple eruptions of color against the monochrome devastation. Ecologists watching this process found themselves witnessing something that textbooks had described, but that no living scientist had observed at this scale. Primary succession. The very beginning of an ecosystem. Life constructing itself from nothing, following pathways that evolution had refined over millions of years specifically for moments like this one. The mountain that had destroyed was also, in its destruction, creating the conditions for something entirely new. This duality, destruction and creation, ending and beginning, is not a poetic invention imposed upon geology by those who need comfort. It is the actual mechanism of how this earth renews itself. Volcanic soils are among the most fertile on the planet. The ash that buried crops and blocked rivers also carried minerals that, once weathered and incorporated into the soil, would make the land around Mount St. Helens extraordinarily productive in the decades to come. The forests that had stood for 2 centuries were gone. The forests that would grow in their place were already beginning. David Johnston had understood this too. He had spoken, in interviews conducted in the weeks before his death, of volcanoes not as destroyers, but as makers, as geological processes essential to the long-term health of landscapes, to the cycling of minerals, to the creation of the soils and the islands and the mountain ranges that make complex life on this planet possible. He had loved volcanoes, not despite their danger, but with full knowledge of it. He had seen them whole, as forces of both ending and beginning. That wholeness of vision was part of what made him exceptional. And it is part of what the mountain took from the world when it fell silent at 8:32 on a Sunday morning in May. The landscape is changed forever, but in the silence, science is already asking its next question. There is a particular obligation that falls upon those who survive, not guilt, not the impossible burden of explaining why one person lived and another did not, but something quieter and more enduring, the responsibility to carry forward what the lost ones knew, to ensure that the knowledge purchased at such cost is not wasted, that the silence left behind becomes, in time, something useful. The volcanology community in the years following May 18, 1980, understood this obligation with great clarity. They went to work. David Johnston had not died leaving behind an empty desk. He had left behind notebooks, reports, measurements taken over weeks of patient, dangerous observation, assessments of the mountain's behavior that had been circulated among colleagues, debated, refined. A body of scientific thinking that was, in the aftermath of the eruption, revealed to have been not merely correct, but prescient. His colleagues at the USGS gathered this material with the care that one brings to something irreplaceable. Because it was. The eruption of Mount St. Helens became, in the years that followed, the most studied volcanic event in history. This was not accidental. It was the direct consequence of the instrumentation that Johnston and his colleagues had installed in the weeks of heightened activity preceding the eruption. Seismographs, tilt meters, gas monitoring equipment, all of it had been recording continuously in the days and hours before the blast. The data that survived gave scientists something unprecedented. A complete portrait of a volcano in the final stages of preparation for a major eruption. Every tremor, every measurable deformation, every fluctuation in the gases escaping from the mountain's vents. For the first time, volcanologists could look at a documented sequence of precursory signals and ask, with real specificity, what does a volcano look like just before it does this? The answer would save lives. Not immediately, not in ways that could be directly traced to a single decision. But over the decades that followed, the patterns identified in the Mount St. Helens data became the foundation for eruption forecasting protocols used around the world. One of the most significant contributions came from the detailed analysis of the lateral blast itself. Johnston had identified the threat of a directional horizontal eruption. His colleagues, studying the physical evidence left across the blast zone, were able to reconstruct the event with extraordinary precision. The angle of the blast, its velocity at different distances from the source, the temperatures reached within the advancing cloud, the relationship between the landslide and the explosive decompression that followed. This reconstruction became a model, not just for understanding what had happened at Mount St. Helens, but for recognizing the potential for similar events at other volcanoes around the world. Volcanoes with steep, unstable flanks. Volcanoes with histories of flank collapse. Volcanoes that had, perhaps, been underestimated because they did not conform to the classical vertical eruption model. There were many such volcanoes. And now, scientists knew what to look for. The monitoring network around Mount St. Helens was rebuilt and expanded in the months after the eruption. Where there had been a handful of observation posts, staffed by rotating teams of scientists, working in conditions of genuine physical danger, there now grew a sophisticated network of remote instruments, seismometers installed directly on the volcanic edifice, GPS receivers capable of measuring ground deformation to within millimeters, gas sensors that could detect the subtle chemical signatures of rising magma long before any surface manifestation appeared. The scientists could listen more carefully, from safer distances. This was, in a direct and traceable way, Johnston's legacy. His death had demonstrated with terrible clarity the limitations of the existing approach to volcanic monitoring. His work had provided the scientific framework for building something better. In 1982, the United States Congress established the Mount St. Helens National Volcanic Monument. 110,000 acres surrounding the mountain were set aside. Not for restoration, not for the replanting of timber or the reconstruction of what had been lost, but for observation, for study, for allowing the landscape to recover on its own terms, in its own time, according to its own logic. It was an unusual decision, a choice to let nature complete what it had begun, without human intervention shaping the outcome. Scientists would watch. They would measure. They would record. But they would not manage. The results exceeded almost every expectation. The recovery of the blast zone became, over the following decades, one of the most important long-term ecological studies ever conducted. Species returned in sequences and patterns that challenged existing theories of succession. Predators followed prey back into the recovering landscape. The lake that formed in the crater, a new lake, entirely new, created by the eruption itself, developed its own ecosystem within years. Life, it turned out, was not merely resilient. It was inventive. The mountain itself was not finished. Between 1980 and 1986, Mount St. Helens continued to erupt, not with the catastrophic violence of that first morning, but in a sustained, measured extrusion of lava that built a new dome within the crater. Scientists watched this process with instruments that Johnston could only have imagined. They mapped it. They modeled it. They used it to refine their understanding of how a volcano rebuilds itself after a major event. And then, in 1986, the mountain went quiet again. For 18 years, it rested. When it awakened again in 2004, the monitoring network was ready. The instruments recorded every tremor, every gas emission, every millimeter of ground deformation. Scientists tracked the new dome's growth with a precision and safety that stood in direct contrast to the improvised, dangerous vigil of 1980. No one died. The science had done its work. A scientist's legacy is not measured in the years of a life. It is measured in what those who follow him are able to do because he existed. By that measure, David Johnston left behind something considerable. There is a building in Vancouver, Washington, that sits quietly on a hill. It does not announce itself dramatically. It does not have the appearance of a place where urgent, consequential work is conducted. From the outside, it resembles what it partly is: an office, a research facility, a place where people go to work in the morning and return home in the evening. But inside, around the clock, every day of the year, someone is watching. The Cascades Volcano Observatory, established by the USGS in 1980 in the immediate aftermath of the eruption, was built on a principle that David Johnston had embodied and that his death had made impossible to ignore. Volcanoes do not respect business hours. They do not wait for Monday morning. They do not announce their intentions in advance. Someone must always be watching. The observatory bears Johnston's influence in ways both formal and deeply personal. Formally, it operates the monitoring networks that his work helped design: the seismometers, the GPS arrays, the gas sensors, the satellite-based deformation measurements that allow scientists today to detect changes in a volcano's behavior that would have been entirely invisible to the instruments available in 1980. Personally, it carries forward a culture of scientific seriousness that those who knew Johnston describe as his most lasting human contribution. A commitment to taking volcanic hazards at their full, undiminished weight. A refusal to minimize what the data is saying because the implications are inconvenient or alarming. Johnston had been willing to say difficult things clearly. The observatory he helped inspire has tried to maintain that standard. The monitoring of the Cascade Range today is a different enterprise entirely from the improvised, courageous vigil of those weeks in the spring of 1980. Dozens of seismometers are embedded in the volcanic edifices themselves, transmitting data continuously to receiving stations where it is processed, analyzed, and compared against known patterns of volcanic behavior. GPS receivers measure ground deformation across the entire volcanic field, detecting the subtle swelling that accompanies the movement of magma at depth, changes measured in millimeters across distances of miles in real time. Aircraft equipped with spectrometers measure the chemical composition of volcanic gases, the ratio of sulfur dioxide to carbon dioxide, the presence of hydrogen sulfide, the subtle shifts in gas chemistry that precede changes in eruptive activity. These measurements can detect the fingerprint of fresh magma rising from depth long before it reaches the surface. Satellites pass overhead on regular schedules, their instruments mapping surface temperature anomalies, ground deformation patterns, ash cloud development. The mountain is watched from above, from below, from every angle simultaneously. What would David Johnston have made of these instruments? Those who knew him, colleagues, friends, fellow scientists who have spent the decades since his death carrying his work forward, tend to answer this question the same way. He would have been delighted, not satisfied. Johnston was not, by temperament, a man who rested in satisfaction. He would have found the limitations of even these sophisticated systems, asked the questions they could not yet answer, pushed for the next generation of instruments, the next refinement of technique. But delighted, yes. Genuinely, deeply pleased to see what had grown from the work he and his colleagues had begun in those improvised, dangerous weeks on the slopes of a waking mountain. The Johnston Ridge Observatory was dedicated in 1997. It sits on the ridge where Coldwater 2 once stood, or rather, where Coldwater 2 no longer stands, where the ridge was scoured to bare rock on the morning of the 18th of May, where nothing remained of the camper and the instruments and the careful notes of a 30-year-old geologist who had chosen to stay at his post. The observatory bears his name. From its windows, visitors look directly into the crater of Mount St. Helens, the same view Johnston had on the last morning of his life, though now framed by glass and accompanied by exhibits explaining the geology, the history, the science that his death helped advance. On clear days, the view is extraordinary. The raw crater, the lava dome within it, the slopes stripped bare by the blast and now slowly, visibly recovering. A landscape in the process of becoming something new, watched over by an institution dedicated to understanding how and why. It is, in its way, a fitting memorial. Not a statue, not a plaque on a wall. A place where science continues. The question that visitors to Johnston Ridge most often ask is not about the geology or the instruments or the technical details of volcanic monitoring. It is simpler than that. They ask, was he afraid? It is a question that resists a simple answer. Fear, for a scientist of Johnston's training and temperament, was not the opposite of courage. It was information. It was data to be processed and responded to appropriately. Johnston had written, in the weeks before his death, that working near an active volcano of this character was like standing next to a dynamite keg with the fuse lit. He knew the danger. He assessed it clearly, without minimization. And he stayed. Not because he did not feel the weight of what he was standing next to, but because the work required someone to stand there, and he was the person best equipped to do it, and that, for a man of his character, was sufficient reason. There are people in every generation who possess this quality, who understand that certain important things cannot be done from a safe distance, who accept the cost of proximity because the alternative, the ignorance that comes from keeping away, carries its own longer-term price. Johnston was one of those people. The observatory on the ridge where he died is, among other things, a reminder that such people exist, that they matter, that the world is measurably different because of them. Today, the Cascade Range holds a dozen potentially active volcanoes, each monitored by networks that owe their existence, in part, to what was learned, at such cost, on a Sunday morning in May of 1980. Mount Rainier, Mount Hood, Mount Shasta. Each of them watched, each of them measured, each of them understood now, with a depth and precision that was simply not available before. Mount St. Helens demonstrated what a volcano of this character could do. The watchers on the ridge have changed. The watching has not stopped. Every story about the Earth is, in the end, a story about time. Not human time, the brief, urgent span of years and decades that we move through with such a vivid sense of consequence, but geological time, deep time, the kind of time that makes a century feel like an afternoon and a human life feel like the space between two heartbeats. Mount St. Helens is, by geological standards, a young volcano. It will erupt again, not as a prediction made to alarm, as a statement of geological fact, offered with the same calm certainty with which we observe that rivers run downhill, and seasons change, and the sun rises each morning over whatever landscape the night has left behind. The question is not whether. The question is when. And thanks to the work of people like David Johnston and those who followed him, the when will not arrive in silence. The mountain has continued to evolve in the decades since 1980. The eruptions of 2004 to 2008 added a new lava dome to the crater, a mass of solidified rock the size of a large office building, extruded slowly and measurably over 4 years of sustained activity. Scientists watched every day of it. They measured every centimeter of growth. They analyzed every sample of gas and rock with instruments that transmitted their findings in real time to researchers on multiple continents. No one was posted 5.5 miles from the crater in a camper trailer.
The instruments were there instead. And the instruments did not need to be brave. They only needed to be precise. Spirit Lake exists again. Not the lake that Harry Truman loved. That lake is gone, buried under the debris of a morning that rearranged the landscape without consultation or apology. But a lake has reformed. The water that accumulated in the basin left by the eruption found its level, settled into the new topography, and began the slow process of becoming a place again. Fish have returned. Birds nest along its banks. On a calm day, the surface of the water reflects the sky above the crater with a clarity that feels, to those who know the history, almost deliberate. Almost like the landscape is demonstrating something. That erasure is not permanent. That even the most complete destruction contains within it the instructions for what comes next. That the earth does not mourn what it has unmade. It simply continues, finding new forms, new equilibria, new expressions of the same ancient processes. This is not comfort, exactly, but it is something. The forest is returning, slowly, on its own terms, according to the logic of succession that ecologists have watched with sustained wonder across 4 decades of careful observation. The stands of young alder and willow that first colonized the blast zone have given way, in places, to the beginnings of conifer forest. Animals whose populations were devastated by the eruption have rebuilt themselves. The elk herds that move through the recovering landscape are larger now than they were in 1980, drawn by the new growth, the open meadows, the particular richness of soil that volcanic material, weathered over decades, eventually provides. The landscape around Mount St. Helens is not the landscape that existed before the eruption. It will never be that landscape again. It is becoming something else, something newer, something that carries the eruption within it the way a scar carries the history of a wound, visibly, permanently, but as part of a living thing that has continued. David Johnston has been gone for more than 4 decades now. He did not marry. He did not have children. He did not live to see the observatory that bears his name, or the monitoring networks that his work helped inspire, or the thousands of people who have stood at Johnston Ridge and looked into the crater of the mountain that took his life. What he left behind is not the kind of legacy that fills a biographical dictionary. It is quieter than that, more diffuse, more difficult to point to with precision. It lives in the protocols followed by volcanologists working tonight at monitoring stations in Indonesia and Japan and Iceland and Chile. In the evacuation plans developed for communities living near active volcanoes on every inhabited continent. In the instruments installed on volcanic flanks in places Johnston never visited, following principles he helped establish. It lives in the lives not lost, because someone, somewhere, took the warning seriously. Because a monitoring network detected the precursory signals in time. Because the science that Johnston practiced with such devotion and at such cost had been refined and extended and applied by those who understood what he had given for it. There is a particular kind of heroism that does not look like heroism from the outside. It does not involve a dramatic decision made in a moment of crisis. It does not announce itself. It accumulates, quietly, over years of careful work and serious thinking, and the willingness to say difficult things clearly, even when clarity is unwelcome. David Johnston's heroism was of this kind. He did not die reaching for glory. He died reaching for a radio, transmitting the last data point of a scientific life conducted with extraordinary integrity, ensuring that the people 57 miles away would know, in time to understand what was happening,
that the mountain had finally done what he had spent months warning it might do. 6 words, spoken calmly, into a radio that would carry them 57 miles south and then fall silent forever. The Earth does not grieve. It does not remember individuals. It does not mark the places where particular human beings made their last stand against its indifference. It continues its processes, its slow drift of plates, its cycling of rock from surface to mantle and back again, its patient accumulation and release of pressure, without reference to the small, brief, luminous lives that unfold across its surface. But we remember. We build observatories on the ridges where scientists died so that others would not have to die in ignorance. We name our instruments and our institutions after those who showed us how to use them. We carry their questions forward into laboratories and field stations and the quiet hours before dawn when a seismograph is recording and someone is watching. This is what science does with its losses. It converts them into knowledge. It ensures that the silence is not the end of the story.